he moved ahead with one of his very famous students, Professor Krishnan, for the discovery of the Raman effect. The instrument which was used then was very, very simple. As the story goes, he actually made a request to the Vice Chancellor of Calcutta University that if I can get a grant of around 300 rupees to buy a spectrometer, maybe we will be able to do something which can make a mark in the field of science. And he was so confident that he said that maybe we can win a Nobel Prize also. I think that is the kind of confidence and spirit which is needed to look at various things also on the scientific scenario today in the country. Then, when he was very sure that he and his group have found really something new worth reporting, he made sure that he is one of the first, tell people that they have observed this, and this is a very interesting result. And later this was known as Raman effect. So he actually sent a telegram to nature that we have observed this kind of observation from the spectra of liquids, and so that there may be the right kind of a time stamp for the discovery itself. He also, called a press conference to tell press people that yes, he has, his group have discovered this particular phenomena. I think it is legendary to really think about these quantum Indians, and they made their mark. Professor S.N. Bose, he was responsible for what we call the idea of bosons, and that was actually noted by Albert Einstein, and that is how he is one of the immortals of physics. And we know that half of the particles found in nature are bosons. And Meghnad Saha was also one of the very interesting scientists on the scenario at that point of time. And you can say that these are the three people who laid the foundations of modern science in the country. Meghnad Saha was one of the first persons to report about the spectra of stars and gave his famous ionization formula. And people in astronomy and astronomical physics give him the credit of starting modern astronomy, and he definitely deserved a Nobel Prize.
Program is going to start.
However, getting nominations, he was nominated many a times for that, was not an easy task.
Check.
Unfortunately,
Sir,
he also died very early. But
Ajit, the program is going to start now.
Aspects
yes.
which are very interesting about Professor
Ajit, sir,
Ahluwalia ji. I think now,
sir, Ahluwalia sir, we are starting the stage program. We are starting the stage program now.
Let us listen to what are the announcements there. Thank you.
Sir, we shall start the stage program now. The guest has arrived. Professor Deshmukh ji has arrived. We shall be starting the stage program now.
I request the honorable dignitaries to please be seated on the stage.
So Professor Deshmukh is here, and I am very happy that to
Ajit Bappa ilonchuru stage program akapa. Ajit kari. Shivraj Ali. You can start by that. They will do it for you. ಈ ಕಡೆ ಬಂದ್ಬಿಡಿ ಪ್ರೇಯರ್ಗೆ ಇಲ್ದಿದ್ರೆ ಅವ್ನು ಮಾಡ್ಕೊತಾನೆ ಆ ಕಡೆ ಮುಂದೆ ಬಂದು ಮಾಡಿ.
Shreya, can you please explain me about photon pulses?
Sana, what are you doing? We are now in front of the curious audience. We shall discuss about that later. Namaste to all. Welcome to
The World of Physics.
I'm Shreya Kumar.
And I'm Sahana Shriyan.
We are students of physics at National College, Basavanagudi.
Now my friend Shreya will begin the session with the prayer.
I request everyone to please stand up for the prayer. यं ब्रह्मा वरुणेन्द्र रुद्रमरुतः स्तुन्वन्ति दिव्यैस्तवैः वेदैः साङ्गपदक्रमोपनिषदैर्गायन्ति यं सामगाः ध्यानावस्थिततद्गतेन मनसा पश्यन्ति यं योगिनः यस्यान्तं न विदुः सुरासुरगणाः देवाय तस्मै नमः नमस्ते सते ते जगत्कारणाय नमस्ते चिते सर्वलोकाश्रयाय नमो द्वैततत्त्वाय मुक्तिप्रदाय नमो ब्रह्मणे व्यापिने शाश्वताय त्वमेकं शरण्यं त्वमेकं वरेण्यं त्वमेकं जगत्पालकं स्वप्रकाशं त्वमेकं जगत्कर्तृपात्रप्रहर्तृ त्वमेकं परं निश्चलं निर्विकल्पं वयं त्वां स्मरामो वयं त्वां भजामः वयं त्वां जगत्साक्षिरूपं नमामः सदेकं निधानं निरालम्बमीशं भवाम्बोधिपोतं शरण्यं व्यजाम्ना योऽन्तः प्रविश्य मम वाचमिमा प्रक्षुप्ता सञ्जीवयद्यखिल शक्तिधरस्वदाम्ना अन्यास्तहस्तचरणश्रवणत्वगादि प्राणानां नमो भगवते पुरुषाय तुभ्यं त्वमेव माता च पिता त्वमेव बन्धुश्च सखा त्वमेव विद्या द्रविणं त्वमेव सर्वं मम देवदेव सर्वे च सुखिनः सन्तु सर्वे सन्तु निरामयाः सर्वे भद्राणि पश्यन्तु मा कश्चित् दुःखभाग् भवेत्. Thank you.
Thank you, Shreya. I now like to request the principal of National College Basavanagudi, Dr. Y.C. Kamala, to address the gathering.
ಆಗಿದೆಯಾ?
ಚೇಂಜ್ ಮಾಡಿ ಅಂದರೆ ಚೇಂಜ್ ಅವ್ರು ಶುರು ಮಾಡ್ತಾರೆ ಅಂದರೆ ಚೇಂಜ್ ಮಾಡಿ.
ಓಕೆ ಓಕೆ ನೀವು ಓಕೆ ಇಲ್ಲೇ ಇರಿ ಸೈಡಲ್ಲಿ. ಗುಡ್ ಈವ್ನಿಂಗ್ ಎವ್ರಿಬಾಡಿ. ಐ ನೌ ರಿಕ್ವೆಸ್ಟ್ ಅವರ್ ಸೆಕ್ರೆಟರಿ ಸರ್. ಎಲ್ಲೋದು? ಹಾಂ ಓಕೆ. ಟುಡೇ ಈಸ್ ಎ ವೆರಿ ಸ್ಪೆಷಲ್ ಡೇ ಫಾರ್ ಅಸ್. ಆಸ್ ವಿ ಆಲ್ ನೋ, ಫ್ರಮ್ 1901 Nobel Prizes are given for science subjects and for economics, medicine and for peace. Starting from Röntgen, who is the first Nobel Prize winner, and till today, that is 2023, various discoveries of physics have been awarded Nobel Prize. I am not going to history of the Nobel Prize. This year's Nobel Prize was given to Attosecond dynamics. That is, sir, I request our president and secretary to come on the dais. Sharmishta madam, please do come. Okay. Yes, Attosecond dynamics is a very important subject. It is very difficult. What is attosecond? Professor Deshmukh ji will explain you later. Microsecond itself is very difficult. Nanosecond is still difficult. -15, -18. How difficult it is, sir will explain. So to have this program under the aegis of, in association with Indian Association of Physics Teachers, when they contacted about a month back, I contacted our management. They happily agreed to conduct this program because we need patronage to conduct good programs. We thank our management for the same. So we have with us Professor P.C. Deshmukh ji. He is a professor at IIT Tirupati and at DSU Bangalore. His detailed descriptions will be given by Madam Sir Mr. Sahu later. Sir, On behalf of National College and on behalf of IAPT, it's my pleasure to have you here and welcome you on our behalf of all of us here. Okay. We have with us our President, Dr.HN Subramaniaji, a medical doctor who is serving our institution from past so many months, and he is very young at heart. To say he is 93 years young. Okay. He is serving us and he is very good in science. Sir, we are very happy to have you here. Thank you very much and we welcome you for the program. Equally dynamic is our secretary, Shri Venkateshiva Reddy sir. Basically, he is an engineer. He has served across the state and across the country in various capacities. So if I start saying, that takes 15 minutes. So he is now serving our institution. Sir, it's my pleasure to have you here and welcome you on behalf of all of us here. And our other secretary, Mr. Arun Kumar sir and Sudhakar Isturi sir, they may join any moment. In their absentia, I welcome them. So we have with us in online, we have Mr. Professor P.K. Ahluwalia ji is already online. Professor Ahluwalia ji, President of the Indian Association of Physics Teacher. He is from Himachal Pradesh. He has joined. We welcome you, sir, on behalf of us. And I have with me Madam Sharmishta Sahu, Secretary for RC12A. She is a physics professor. She has written a lot of textbooks. And she was a professor at MLA College. She has written textbooks and she keeps conducting large number of workshops across the country, not in just Bangalore. Okay, we welcome her. Right now in front of me, I have luminaries. We have Professor Srikanta, Professor Subramaniam. So they have a country level exposure for the subject of physics. So we welcome you also. All the physics professors are present here. And I have, Sir Ramesh, sir, please come on, dais. Bani, bega bani. We have our Vice Principal, Mr. Dr. Ramesh. I welcome Dr. Ramesh on behalf of everybody. The program is for the students and the teachers. We need to update ourselves. All the students and teachers have participated with enthusiasm here. I welcome one and all of you. And here there are teachers from other colleges also. Just now I saw a group of students and teachers coming from Rajajinagar. Please raise your hand. Okay, they have all come from Rajajinagar. The madam has also come. Madam, welcome you also. With this, I conclude my welcome address. Over to the comparers. Thank you.
Thank you, ma'am. Now I request the Honorable President and Secretary of National Education Society, Karnataka, to speak a few words.
With a excuse from you, I talk only in Kannada because ಸನ್ಮಾನ್ಯ ಪ್ರೊಫೆಸರ್ P.K. ಅಹ್ಲುವಾಲಿಯಾರವರೇ ಮತ್ತು ವೇದಿಕೆಯ ಮೇಲೆ ನನ್ನ ಜೊತೆಯಲ್ಲಿ ಆಸೀನರಾಗಿರ್ತಕ್ಕಂಥ ಎಲ್ಲ ಗಣ್ಯ ವ್ಯಕ್ತಿಗಳೇ ಮತ್ತು ಡಾಕ್ಟರ್ P.C. ದೇಶ್ಮುಖ್ರವರೇ ಮತ್ತು ಇಲ್ಲಿ ಸಭಾಂಗಣದಲ್ಲಿ ನೆಲೆಸಿರ್ತಕ್ಕಂಥ ತುಂಬ ವಿದ್ವತ್ ಜನರ ಸಮೂಹ ಅಂತ ಹೇಳಿದರೆ ತಪ್ಪಾಗಲಾರದು. ಯಾಕೆಂದರೆ ಹೈಯೆಸ್ಟ್ ಲೆವೆಲ್ ಆಫ್ ಫಿಸಿಕ್ಸ್ಗೆ ನೀವು ಎಲ್ಲ ತಲುಪಿದ್ದೀರಾ. ಇನ್ನೂ ಬೇಕಾದಷ್ಟು ಸಂಶೋಧನೆ ಮಾಡ್ತಕ್ಕಂಥ ಅವಶ್ಯಕತೆ ನಿಮ್ಮಲ್ಲಿ ಹಲವಾರು ಜನಕ್ಕೆ ಇರಬಹುದು ಅಂತ ನಾನು ಭಾವಿಸ್ತೀನಿ. ಏನೊಂದು ಪ್ರಪಂಚದಲ್ಲಿ ಅಚೀವ್ ಮಾಡಬೇಕಾದ್ರೆ ಬಹಳ ಮಟ್ಟಿಗೆ ಫಿಸಿಕ್ಸು, ಬೇರೆ ಸಬ್ಜೆಕ್ಟ್ಸು ಇಲ್ಲ ಅಂತ ನಾನು ಹೇಳೋದಿಲ್ಲ. ಈಗ ಮೊನ್ನೆ ಚಂದ್ರಯಾನದ ಉಪಗ್ರಹಕ್ಕೆ ಮೂಲ ಕಾರಣವೇ ಫಿಸಿಕ್ಸು. ಈ ಫಿಸಿಕ್ಸ್ ಇಲ್ಲದೇ ಇದ್ದ ಪಕ್ಷದಲ್ಲಿ ಅನೇಕ ವಿಷಯಗಳು ಬ್ಲ್ಯಾಂಕ್ ಆಗಿಬಿಡುತ್ತವೆ. ಆದ್ದರಿಂದ ಫಿಸಿಕ್ಸನ್ನು ತೆಗೆದುಕೊಂಡು ಓದ್ತಾ ಇರ್ತಕ್ಕಂಥವ್ರಿಗೆ, ಪಾಠ ಹೇಳ್ತಾ ಇರ್ತಕ್ಕಂಥ ಎಲ್ಲ ಗಣ್ಯಾತಿ ಗಣ್ಯ ಉಪಾಧ್ಯಾಯ ಮಿತ್ರರಿಗೆ, ಸಮಸ್ತ ಜನಕ್ಕೂ ನನ್ನ ಅಭಿನಂದನೆಗಳನ್ನು ನಾನು ತಿಳಿಸ್ತಾ, ಇವತ್ತು ನಾವು ಮಾತಾಡ್ತಕ್ಕಂಥದ್ದು ಏನೂ ಇಲ್ಲ. ಯಾಕೆಂದರೆ ಐ ಆಮ್ ಎ ಮೆಡಿಕಲ್ ಡಾಕ್ಟರ್ ಆ್ಯಂಡ್ ಅವರ್ ಸೆಕ್ರೆಟರಿ ಈಸ್ ಅನ್ ಇಂಜಿನಿಯರ್, ಎಲೆಕ್ಟ್ರಿಕಲ್ ಇಂಜಿನಿಯರ್. ಸೊ ವಿ ಡು ನಾಟ್ ನೋ, ವಿ know zero about physics. We simply keep quiet and listen to our guests. That's all. Thanking you for giving me the opportunity to speak a few words. Shubha Namaskara. Namaskar.
Sharmishta ma'am, you'll give his introduction. Quick. His introduction. Deshmukh. Will do, na?
Thank you for your appreciative words, sir. I request the respected chairperson, Professor P.K. Ahluwalia, to share an introduction of Professor P.C. Deshmukh.
Good evening. Am I audible?
You are, sir. You are
Yes,
audible.
sir.
Well, okay. Thank you very much. First of all, my greetings to the dignitaries sitting on the dais, and to my very dear friend, Professor P.C. Deshmukh, Professor Kamla, Ma'am Sharmishta, and the other faculty members who are in the hall, and the students who have come to listen to this very important lecture. Dear friends, we have started a new initiative from Indian Association of Physics Teachers that every year we will hold Nobel lectures on physics by some expert who has worked in that area. And I am very glad to tell the audience here that Professor P.C. Deshmukh is one of those persons who has, in fact, worked in this area. And the Nobel laureates who have got this year's Nobel Prize have cited his work also in their papers. So that is the reason that we are very happy to be part of this lecture. Professor P.C. Deshmukh has been very active member of our Indian Association of Physics Teachers. He has great passion for not only physics research, but he also is a very passionate teacher. And that is, in fact, evident in his two very scholarly books which he has written. One on the foundations of classical mechanics, and the recently released book on quantum mechanics. Both the books have been published by Cambridge University Press, and we are happy to tell you that both the books were released in the Indian Association of Physics Teachers conventions. The first book was released in Allahabad, and the second book has been released in Jaipur. So congratulations, Professor Deshmukh, for this great work which you have done, keeping in mind that the quality of education, particularly physics education, needs to be increased. My personal feeling is this, that both these books on the Indian physics scenario are going to be there for quite some time, because these are the books which are not only talking about things which are classical, but talking about those things which are, in fact, something very, very new. He touches upon in his quantum mechanics book the latest topics of entanglement and quantum computing, the algebra of qubits, and so on. And I think this should excite very many people. Let me also tell the audience that Professor P.C. Deshmukh is former professor of IIT Madras. He did his PhD from the University of Nagpur, and he is basically a theoretical physicist. But after, retirement from IIT Madras, he is one of those persons who would not sit idle. And he decided to be part of a very important initiative in IIT Tirupati. And this is basically where he is presently leading a Center for Atomic, Molecular and Optical Sciences and Technologies. In short, it is called CHEMOST. And he is simultaneously an adjunct professor at two places. One is at IIT Tirupati and other is at IISER Tirupati. And I was, in fact, one of the participants in a very interesting lectures seminar series which Professor Deshmukh curated for the young audience in the country. And that was on the disruptive technologies which are likely to be there because of the latest happenings in the field of quantum mechanics. And I'm very happy to welcome you, sir. And we are looking forward to your wonderful lecture. Let me assure the audience here, the topic may be tough, but Professor Deshmukh is known for making it simple and understandable. He's a wonderful public speaker. Welcome, sir, and greetings on this day of very specific, importance for Indian physics, that we are celebrating Professor C.V. Raman's birthday. And it is in the fitness of things that talking about a Nobel Prize this year, we are hosting this lecture in a college and on this auspicious day. Thank you very much.
Thank you, sir. Sahana, do you remember you were asking me a doubt about attosecond physics in the beginning of the program? Now all your doubts are going to be cleared.
How?
It's now the time for the most awaited talk. The talk on attosecond dynamics, the Nobel Prize in Physics 2023 by Professor P.C. Deshmukh. Over to you, sir.
I also welcome Madam Deshmukh for coming over here for the program. Welcome, ma'am.
Thank you. Please continue. Thank you. Sir, is it fine to use the mic? You keep in the pocket. One second. I'll just lose it. Are we ready? Am I ready? Okay, greetings and namaskar to everybody. I think I'm now fully armed to give a talk with my microphone and everything set up. Thank you for getting me here. And you expected your doubts on attoseconds to be resolved in my talk. And I'm going to bring my own doubts to the talk. Very privileged to be here at the National College. I've heard that many eminent educationists have come out of this college. So I'm really very excited to be here. So thank you very much to the organizers for getting me here. When I came, Professor Ahluwalia was talking about Meghnad Saha's work, and I would have loved to just sit down and continue to listen to him. So Professor Ahluwalia, thank you very much. Let me jump into the topic. So Ferenc Krauss, Anna Leweiler, Pierre Agostini were awarded the Nobel Prize this year in physics. And we will talk about this. So today's talk, as Professor Ahluwalia also commented, it is a tribute to Professor Chandrasekhar Venkat Raman. On his birthday, actually, he would have been 135 years today. It is his birth anniversary. This picture on the right is at the Nobel ceremony that he attended in Sweden. You also see his pictures with some politicians sometimes, but he was not very fond of politicians. In fact, he had a board on the gate of his house which said that dogs and politicians are not allowed in. He was not very fond of that, and it has been suggested that he was awarded the Bharat Ratna in 1954. He was one of the first recipients of the Bharat Ratna, along with Dr. Sarvepalli Radhakrishnan and Chakravarti Rajgopalachari in 1954. And it is suggested that part of the reason he was awarded was to appease him because he was very critical of the political establishment. I will like to quote Raman before I enter this topic of attosecond dynamics. He was a firm believer of teaching in vernacular languages, in local languages, in mother tongue. And I was very thrilled to hear this talk in Kannada. Just as we started this program, it was very appropriate, I would think. He always said that science must be taught in mother tongue, and I strongly support this view myself. Another quote I would like to begin with, to comment on, that the true wealth of a nation consists not in the stored up gold, but in the intellectual and physical strength of its people. So, very inspiring personality, and it's a great privilege to be having this festival today on Professor Raman's birthday. So these are the three distinguished scientists, Ferenc Krauss, Anna Leweiler, Pierre Agostini, who were awarded the Nobel Prize this year. And let us try to get some idea about what an attosecond is. So everybody knows the age of the universe. It is about 13.8 billion years. If you convert this into seconds, it is about 10 to the power 17 seconds. More than 4 times 10 to the power 17 seconds. An attosecond is a very tiny unit of time. So the number of attoseconds in 1 second is 10 to the power 18. So if you look at the reciprocal of the age of the universe, it would be 10 to the minus 18, 10 to the minus 17. And an attoseconds is 10 to the power minus 18 seconds. It's a very, very tiny bit of time interval. And it is for this work that the Nobel Prize has been awarded. So you can imagine what a huge task, what a big experimental challenge it must be to produce light pulses using lasers to generate tiny bits of tiny laser pulses of such short duration. Now, all of you are familiar with the stroboscopic effect. If you're looking at a rotating fan and its blades have colors, you're not always able to distinguish between them because the blades are turning too fast, too rapidly. And depending on the speed of the shutter speed, means you're looking at it using your eyes, you could use it using a very fast camera if you like. And if you used an extremely fast shutter speed camera, you can probably resolve the colors. And depending on the duration of an event, you really need extremely fast cameras. So, to get an idea about what happens in an attosecond, like everybody knows that the speed of light is 10 to the 8 meters per second. And the time that light travels in 1 attosecond is about an angstrom. So on atomic time scales, if you want to see motion on an atomic time scale, then you need something, you need a source of light, pulses, which will have attosecond duration. If you look at the time period for an electron in the hydrogen atom's Bohr orbit, the ground state of the hydrogen atom, it takes about 150 attoseconds. But mind you, the electron is not like a point particle. This is an idea which worked for many centuries to describe charges as particles. But then it is now about 100 years that people realized that the description of physical entities in nature in terms of either waves or particles is not very easy. There is a certain duality that you are confronted with. And what happens is that you need to consider what are called as wave packets. And you're really looking not at a particle which is rotating in circular or elliptic orbits. That model belongs to what is called as old quantum theory. And it is really not a valid model. It has been superseded by quantum mechanics. And orbits as such lose their significance completely. You have wave packets, and what is happening inside the atom is a wave packet which moves from one part of the atom to another part of the atom. And if you're looking at this kind of motion, then it is very rapid. And you need a camera with a shutter speed which is extremely high. So if the wave packet density moves from one part of the atom to another part of the atom, it happens on a scale of an attosecond or 10 attoseconds or 20 attoseconds and thereabout. So we all have an idea about a second. A millisecond is typically the shutter speed of many cameras. If you look at electronic circuits, then fast electronics takes place on time scales of the order of a nanosecond, 10 to the minus 9. Going to shorter time scale events, molecular vibrations occur at a picosecond durations, photosynthesis at a femtosecond, 10 to the minus 15, and electron dynamics, wave packet movements inside atoms on a scale of 10 to the minus 18 seconds. So it's a very, very short duration of time. And I will invite you to go through some original literature. This is achieved using what is called as high harmonic generation, HHG, in which you use femtosecond lasers to initiate the process, but then you achieve pulses which are 1,000 times quicker on the attosecond scale. So this is one of the key papers by Paul Corkum and Annelie Wheeler, who is one of the Nobel laureates. And this has led to a completely new domain of spectroscopy, which is ultrafast spectroscopy. You need very strong laser intensity for this, which is of the order of the intensity of electrical fields inside an atom. So let me begin with the photoionization experiment, which I suppose all are familiar with. If you shine light on a metal surface or on an atom, you can kick out an electron. And this was explained by Albert Einstein in 1905, for which he was awarded the Nobel Prize. And the experiments were done earlier in the 19th century by Hertz, later verified by Leonard. But this happens above the ionization threshold, because if the electrons are bound to the nucleus, the photon energy must have an energy which is more than the ionization threshold. We are talking about ionization below the threshold. Now, this is very interesting, and it is a completely quantum phenomenon. This takes place due to what is called as tunneling. So there is a barrier, and the energy which is imparted by a single photon is not sufficient to knock out an electron. But many of these photons can work together coherently, and they could enable tunneling of the electron, which is called as the tunnel effect in quantum mechanics. It's referred to as under the barrier penetration. And what you see in the picture is an electron in the Coulomb field, which is this is a one-dimensional picture, and then it overcomes this barrier. Can you see the cursor, everybody? Yes. So it doesn't have enough energy to overcome the barrier, but it tunnels through the barrier. And this is the beginning of the generation of attosecond pulses. This is the first of a series of few steps. And these steps are categorized, largely speaking, in 3 steps. This is the first of the 3 steps in the higher harmonic generation process. And using this, the original frequency can be enhanced a number of times, 10 times, 20 times, or even 100 times. And that is the kind of gain that you can get. So beginning with femtosecond lasers, you need a huge amount of energy to achieve this. You need intensities of the order of 10 to the 14 watts per square centimeter. And if you compare it with the energy generated at a nuclear plant, which is 10 to the 9 watts per square centimeter. So you need very short pulses. Has this gone off? I need some technical help here. Okay, is it? All right, I think it is back. Yeah. So this three-step model has been developed by Paul Corkum, a very distinguished physicist. And the three major steps are that when you shine this laser pulse, which is of femtosecond laser, and you shine it on atoms like gaseous atoms in a gas phase, then the electric field of the laser adds up to the atomic potential. And the atomic potential is essentially coulombic. It has got the shape that you see by the dotted curve. But this is then modified because of the laser. And you get a field which is indicated by the dashed slanted line, as a result of which tunneling becomes possible. So this is the first step, tunneling ionization. The wave packet escapes, but not fully, because it takes time, no matter how short it is. No matter how short the time is, it takes some time. And what happens is that the part of the wave packet which has escaped, which has tunneled through, the complete wave packet has not escaped, but a part of it has escaped. And while it is moving away from the atom, the direction of the electric field of the original laser reverses. And then the electron, which is moving away from the atom, is attracted back toward the atom. Now this is amazing, because the electron which is escaping, but the driving field changes its direction. You know that electromagnetic waves are oscillatory, and the electric and the magnetic vectors, they execute sinusoidal motion. So the direction of the electric field reverses, as a result of which the force on the escaping electron reverses, and it is attracted back toward the atom. And this wave packet, which is moving away, turns over. It is a returning wave packet, and it can recollide with the parent atom from which it escaped. Now it may recollide, and then what happens? It may get trapped again. And when it gets bound once again, then it has acquired a good amount of kinetic energy during its travel, and that kinetic energy has to be released. So that gets released as attosecond pulses. This is at a frequency which is much higher. You generate attosecond pulses of higher harmonics, and through this recollision. So these are the three major steps which have been explained very nicely by Paul Corkum. And when this kinetic energy is released, it comes out as attosecond pulses through superpositions of many different frequencies. Now, the tunneling probability is highest at the peak. So this is a very nonlinear process. It's a very nonlinear process. So, which is why the half cycle becomes a very important thing, because at every half cycle, you have got a maximum of the electric vector amplitude, either maximum or negative maximum in one direction or the other. So to understand this process, I would like to go back to the Young's double slit experiment, which many of you may be familiar with. And if you have an electron gun, and it has the possibility of passing through two slits, and then find itself on a detector. So whenever nature has got alternatives in front of it, you always see interference. So this is a very remarkable thing, and it is essentially the fundamental principle in quantum mechanics. In fact, almost the entire essence of quantum mechanics is contained in this principle, that when alternatives exist, there is interference. And what you see on the detector is bright and dark fringes. Even if the release of electron from the electron gun is so slow that there can be only one electron in the apparatus at a time. So when you think of a single electron, you think of it as a particle, you think that it would have gone either from slit 1 or slit 2. And at the detector, you certainly detect a particle. But then, as the experiment progresses, after sufficient number of electrons are detected, you will find that most of them gets concentrated alternatively in bright and dark fringes. Now the same thing is happening over here. And here is an explanation of this from Paul Corkum himself. This is a snapshot from his talk, which I will urge you to watch. It's a wonderful lecture, which is available on the YouTube, the Technion lecture. If you just Google this, I'm very sure you can find it very easily. You will find this image at 23 minutes 31 seconds in his talk. And he's explaining this tunneling and returning wave packet. When the returning wave packet overlaps with the part of the wave packet which has not escaped. So that's the point I was making, that when the wave packet tunnels out, only a part of it escapes, not all of it. There is a little part which is still left behind. And the returning packet overlaps with it, generating certain coherent phenomena which give rise to high frequency, high harmonic frequency generation. And the process of tunneling effectively acts like a beam splitter, like in a Mach-Zehnder interferometer. What you have is, or for that matter, even the Young's double slit experiment in a certain sense is a beam splitter, because you've got an incident electron wave, and then it has got the option to go either from slit 1 or slit 2. So a part which is left behind interferes with the returning wave packet, and that is the coherent superposition of this, which gives rise to attosecond pulses. And what happens through the superpositions of waves, some of you would have studied Fourier analysis, and you know that when waves, simple harmonic waves of different frequencies overlap and they get superposed on each other, they may constructively interfere or they may destructively interfere. And depending on how the mathematics of Fourier analysis works out, you may get pulses. In this case, Professor Anne Leveilleur was able to generate attosecond pulses. These are pulses which last for about 20 attoseconds. So this is the picture of superposition. You will see it on the website of the Nobel Prize in Physics for this year. And you have these marvelous generations of attosecond pulses which come as a result of superpositions of these number of sinusoidal variations. Now, Paul Agostini, he managed to do calibration, because how do you measure this? How do you calibrate it? Means you need a reference as well. So I will not go into the experimental details, but Agostini, he split the original laser, infrared laser, and you see this over here. This is the path of the original laser. You have got a beam splitter. So part of it goes from here and goes through a certain delay, whereas another part goes on this track and goes through this gas through which this tunneling and returning wave packet is generating high harmonics. And when they re-interfere, you can do the calibration and you can find out what exactly is the duration of these pulses. So Augustini made extremely important contribution to this, this experimental setup. It's an awesome experiment. So I will come to the work of Ferenc Krauss as well. But you see, Paul Corkum is a theorist. Later on, he also did some experiments. He's the one who developed this three-step model. And these three got what is called as the Wolf Prize last year in 2022. And many consider the Wolf Prize as a pointer toward the next year's Nobel Prize, because this has happened in the past. People who got the Wolf Prize in 1 year ended up getting the Nobel Prize the next year. So many people who work in this field thought that Paul Corkum would get a Nobel Prize. But then the Nobel Committee decided to concentrate on the experimental science, the experimental achievements, to which Augustini made important contributions, as I said, and the Nobel Prize for 23 has been awarded to Ferenc Krauss, Anna Levelier, and Pierre Augustini. Krauss did some very nice experiments also. He used attosecond pulses to carry out subsequent photoionization, measured the time delay in photoionization. I will come to that a little bit later. But he essentially measured that there is a time delay, because at the time of Einstein's explanation of the photoelectric effect, it had one considered the photoionization to be an instantaneous process, that as soon as a photon is absorbed, an electron is knocked out if it is above the threshold. But there is a little bit of delay, and Ferenc Krauss measured the time delay between ionization from the 2p shell of neon compared to the photoionization from 2s subshell of neon. And the difference in the time delay was of the order of 21 attoseconds, some plus or minus 6 seconds and so on. So these are extremely short durations of time. And if you look at the previous best, this was 1,000 times longer durations. This was femtosecond, 10 to the minus 15. And this also was awarded a Nobel Prize. This was the 2018 Nobel Prize 5 years ago, which was awarded to Arthur Ashkin and Morrow and Donna Strickland for generating ultrasonic optical pulses. So these were of femtosecond duration. This itself was a huge achievement, and people thought that, okay, it will be very difficult to get shorter pulses. But this was a huge achievement. It has impacted technology in a big way. In fact, in medical sciences, it is now used in eye surgeries. This femtosecond pulse generation is achieved through what is called as CPA, the chirped pulse amplification. And here, the problem is that if you try to amplify short pulses, you need a certain medium, and the medium can get damaged by intense bursts of light. So you have to be able to avoid that. And this is achieved in this chirped pulse amplification scheme by using these double grating, the grating pair pulses. So the first grating, which you see over here in this blue circle. So here, it disperses it temporally and spectrally. It stretches out a pulse. And it is this stretched pulse which is amplified, and then it is recompressed using a similar assembly of double grating. So this is a beautiful technique for which the 2018 Nobel Prize was awarded. But now we have this high harmonic generation, and I pointed out that you have got the tunneling which takes place first. The wave packet which tunnels out. So this is the first step. You have the wave packet in the atomic field, which is mostly Coulombic. And then, as a result of the laser intensity, you have sufficient energy to enable the wave packet to escape. Part of the wave packet escapes, but then the direction of the electric field of the laser reverses and the electron wave packet is attracted back. So this is the technique which is being used, and then it releases the kinetic energy that it had gained as these high harmonics whose superpositions generate attosecond pulses. So you get number of different frequencies, and there are some numbers which Paul Corkum is pointing out. These numbers are just illustrative. They are not to be taken seriously. They are only to illustrate the idea that you get high harmonics of several different energies at different multiples of frequency of the original laser. And what color you will get depends on what time the wave packet escapes, or part of the wave packet escapes. So these are simulations, these are computer simulations of this process. And if you look at the time scale which is at the bottom, these are in some units, so don't worry about the units, but between 0 and 0.5, if they escape, then there is a chance that they will escape, travel, become returning wave packets, get attracted back toward the atom, recollide with the atom, get superposed with the leftover wave packet, and generate higher harmonics. So this is what can happen. Not all wave packets which escape will return. Some of them will just escape. They will just wiggle away, and there is certain energy dynamics which has to be taken into consideration, because there is a certain maximum energy which can be released in this process. And this can be estimated using sophisticated mathematics, which I will not get into. You have to get into the ponderomotive force and so on. But some wave packets wiggle away. Not everything gets superposed with the original wave packet. And everything depends on at what time of the original wave packet this escape takes place. So if it is, like I mentioned, in certain situations, when it tunnels out, that is what is being referred to in this picture as the birth of the wave packet. And in some cases, they get recaptured through a returning wave packet reabsorption. And so there is a moment of birth and a moment of recapture, and it all depends on what color you get, depends on when the tunneling takes place and when it is recaptured. So if there is a later birth, earlier is the recollision and lower the frequency toward red, but if it is later, then you get toward green or violet and so on. And then all of these colors, they get superposed to generate attosecond pulses. So as I mentioned, the tunneling itself is a very nonlinear process because it depends on the intensity of the laser, and that is changing rapidly. So it takes place maximum when it is at the peak at half cycles. The techniques have got very interesting names. You will remember visiting a zoo. One technique is called as rabbit, reconstruction of attosecond beating by interference of 2 photon transitions. There is also a frog crab, frequency resolved optical gating for complete reconstruction of attosecond bursts. These are extremely sophisticated techniques which people have developed, and very appropriately, it has been awarded the Nobel Prize. This is the experiment I was referring to earlier, which is the experiment of Ferenc Krauss on neon photoionization. And here is a departure from the Einstein photoelectric effect as we knew it from 1905, where it was considered to be instantaneous. And if the photoelectron ejection takes a little bit of time, no matter how short it is, then it is not the same for photoionization from different shells. And the time delay difference between photoionization from the 2p subshell of neon and the 2s subshell of neon is of the order of 21 attoseconds. And my students Ankur Mandal and Samajit Saha were very quick to get interested in these problems. So they studied time delay in autoionization, in photoionization processes. This paper by Ferenc Krauss is in 2010. Ankur and Samajit wrote this paper in 2014. Soon after this, about 4 years later, they were PhD students at the IIT Madras. And I will refer to their results in the context of another work which is carried out by another Nobel laureate. As I mentioned, there are 3 Nobel laureates. Professor Anne Huillier is one of them. And she studied photoionization from xenon, from the 4D shells of xenon. And the 4D in xenon is spin orbit split, because in addition to the orbital angular momentum, the electron also has got a spin angular momentum. And you have what is essentially a relativistic splitting of the 4D into 4D 3/2 and 4D 5/2 levels. Samajit, in fact, went on to do a postdoctoral work with Eva Lindroth, who was one of the authors along with Anne Weyler. This is her reception after the Nobel Prize was announced, and one can imagine the excitement in a university when somebody on your faculty gets awarded by something like a Nobel Prize. And this is their paper, the Eva Lindroth, Wheeler. There are many others in this collaboration. You see the names of all the authors over here. This is the paper in 2020, Nature Communication. And what they study is, the wave packet dynamics. This thing is getting timed out, or I don't know what is it. There is some time delay here as well. So when an electron gets knocked out of the atom, the electron is, we think of it as a single particle, but then it has its dynamics connected with the dynamics of all the other electrons. And you really cannot put your finger on any electron that this is electron A, electron B, and so on. Earlier, Professor Ahluwalia ji was also talking about Bose's work. So these quantum particles are indistinguishable, and they are either fermions or bosons. And electrons are fermions, so they cannot really be numbered. You cannot put your finger on one particle or the other. And their dynamics is correlated and also affected by all the intrinsic properties of the electrons, which includes an intrinsic angular momentum, which is spin. And the spin-orbit interaction has consequences which become manifest on the attosecond level. So these are the measurements which were carried out by Professor Anne Levelier. So this is, yeah. Yeah, is it coming back? All right. So when you have a vacancy in the 4D shell, it can be either in the 4D 3/2 or in the 4D 5/2 sublevels, because these are spin orbit split doublets. You can have photoionization and a photoelectron can escape into the continuum. But you may also have other processes like the OJ effect and so on. A 5s electron can drop into the vacancy. The energy difference can kick out 5p electron. And there is very complex dynamics which is taking place in the atom. So there is nothing like a single process. And as we know very well, as I mentioned earlier also, that when nature has access to multiple events, like a particle going through the Young's double slit experiment, there are multiple possibilities. So here you can have photoionization, the photoelectron can escape, this is one possibility. The OJ transitions is another possibility. So there are many things which can happen during the rearrangements. And when you have these rearrangements, you see quantum interference. And this will have measurable effect on the experiments that you carry out. And it impacts the time delay, the time that is taken by the 4D electrons to come out of the atom. And this delay gets affected. So it depends on the energy at which this is taking place, because it is a resonant effect. There are certain things which are happening which are degenerate processes, multiple possibilities at specific energies. So if you measure the time delay at somewhat higher energies, then the photoelectron from the 4D 5/2 and from the 4D 3/2, they come out with the same delay. There is no difference between them. But if it is closer to the ionization threshold, in the range of 75 to 80 electron volts, then there is a delay of about 100 attoseconds. And this has been checked by carrying out certain calculations. You need very sophisticated calculations which take into account these correlations, because this cannot be described using quantum mechanics of single particles. So you need a many-body theory. You also need a relativistic many-body theory. And these are very sophisticated theories. So using a theory which is called as the relativistic random phase approximation, which takes into account the relativistic spin orbit effects, Levillier's group figured out that the time delays in the 4D 5/2 and 4D 3/2 could be accounted for in terms of the spin dynamics. Their method of carrying out relativistic random phase approximation is, they compared with the work of Mandal, who I mentioned. This is Ankur Mandal from IIT Madras. And the references 35 and 36 are to these papers by Ankur Mandal and Swamijit Saha, in which they carried out RRPA calculations with which and Levillier's results were compared. This work goes back to an earlier study which was carried out by Sunil and Tanima in my research group, in which they studied, if you see the figure on the left side, you see a little bit kink. And whenever we talk about this result, we refer to this as the kink result, because this kink really troubled us. We were not sure if it was real, and if there was a kink, what was the reason. And Sunil studied this in great details, Sunil and Tanima. And this study was carried out using a fully relativistic random phase approximation, which has been developed by Walter Johnson along with Delgarno at Harvard. And this technique, so this is the full-scale relativistic RPA, the one which Professor Anne Levillier has used is basically, it begins with relativistic calculations and puts in the correlation, which is more or less equivalent to the relativistic RPA, but using a different approximation, which I will not get into. So this is the kink result, and it is this which is responsible for the difference in the time delay between photoelectrons from the 4D 3/2 and the 4D 5/2 subshells. Ankur also did angle-dependent time delay studies. Somajit and Ankul carried out extensive work, which was also referred to in the work of Anne Lewiller. The fully relativistic random phase approximation takes into account certain correlations. And this picture illustrates the kind of correlations which are taken into account in terms of Feynman diagrams. So basically it includes correlations in the initial state and also in the final state, in the ground state, in the initial state. So these are referred to as time backward ring diagrams and also time forward ring diagrams. So all of these are taken into account in the relativistic RPA. There was a paper about a year ago, October 2022, which is available on the archives, I think, and in which a question was raised if Wigner time delay, as it is called, the atomic time delay, is called as the Wigner time delay, if it can actually be measured at all, because in most of the experiments, you really measure effects of the amplitude. So the phase and the amplitude are two important parameters in any interference experiment. So the amplitude leads to certain cross sections and variations in the cross sections, which are always easier to see. The effect of phase is a little difficult one, and whether information about phase is carried at all in a photoionization event is a question which was raised in this paper by Fetich, Becker, and Milosevic. And we have responded to this paper, which is currently with the referees, which will hopefully eventually be published. And it is related to what is called as the Wigner time delay in atomic scattering. And this Wigner time delay, it turns out, is measured in terms of the energy derivative of the phase which is involved in the transition matrix element in a photoionization event. Now, the original theory of Wigner was for scattering, but what makes it applicable, and that was the question which was raised in the previous paper on archive which I mentioned, it is possible, not only possible, it actually happens that it is in a photoionization event, the wave packet of the photoelectron actually does carry that information about the phase, because the two processes are related by a symmetry, which in this case is the time reversal symmetry. So I see a number of students in this hall, and I would like to invite their attention to the importance of symmetry in nature, because it really plays, it is a cornerstone of modern physics. Many things occur because of certain conservation laws, which in turn are related to symmetry considerations. There are different kinds of symmetries: rotational symmetry, dynamical symmetry, parity, reflection, and so on. So the one that we are referring to is the time reversal symmetry, and it is this which connects the photoionization to a scattering phenomenon. So you have an escaping photoelectron, but before the photon is absorbed, it did not exist as a free wave packet. And that is understood in terms of the time reversal symmetry. So I will conclude my talk over here by thanking all my collaborators. So this is the slide in which you see the relationship between collision and photoionization. In a collision, you have an incident wave of electron beam which gets scattered by a target potential. But in a photoionization, you do not have a wave packet in the before the photon is absorbed. It does not exist as a free electron. But then the two are related to each other through different boundary conditions used in terms of the time reversal symmetry. So the relativistic random phase approximation provides a very noteworthy measure of these time delays, which is often used in the analysis of these experiments. I would like to thank my collaborators. There are many who have contributed to this. Thank you very much. I will be happy to take some questions. Yes, please.
You said that the wave packets, they tunnel partially, partial tunneling will be there.
Yes.
And some of them, the part of it will come back and collide with the other wave packet,
Yes.
resulting in the attosecond wave pulse.
Yeah.
But then, and also some wave packets wiggle away, right? Wiggle away, right? What percentage of wave packets really result in this?
I don't know.
Any idea about that?
No, I don't know. I don't think it is easy to talk in terms of percentages and so on.
What's the probability of, let's say?
Yeah.
No, not the percentage. I would say, what is the probability of
the probability is very nonlinear. It is very nonlinear. The tunneling probability is maximum when the laser intensity, when the laser amplitude is at its peak. So there are two peaks, one on the positive side and the other on the negative side. So when it is at the positive maximum or the negative maximum, that is when the tunneling probability is maximum. And it is not easy to really talk in terms of fractions and so on, because our mindset is still thinking in terms of classical mechanics. And that is really not applicable to wave packets.
No, but still we can come out of some probability, no? Because it's a quantum.
Yeah, the probability.
Probability is essentially a quantum mechanical.
It is.
phenomenon.
It is. So as a result of this probabilistic tunneling,
Yeah.
there is a certain probability, certain chance that it comes back. And when it recombines with this, that is when you get attosecond pulses.
Okay, thank you.
Yes.
Sir, you said that the escaped wave packet recollides with the wave packet that hasn't escaped, and this causes the attoseconds. And when this attosecond pulses are used to do more photoionization, the time delay was measured to be 21 attoseconds.
Yes.
I didn't understand how it can do more photoionization.
Well, what comes out as high harmonic generation is also light. And that is light of a much higher frequency. It is light, which is why it is called as high harmonic generation. And you can get light which is much more energetic, which will have sufficient energy to knock out an electron from an atom. So for photoionization, this is the above threshold ionization which you can achieve using these attosecond pulses which are coming out of this process. And that is the experiment that I was referring to with reference to xenon.
Sir, and the time delay part,
And then how much time does the electron need to come out of the atom? Because as soon as the light is absorbed, it is not instantaneous that an electron is knocked out. It takes a little bit of time. And this was not taken into consideration in the 1905 explanation of the photoelectric effect by Albert Einstein.
yes, sir. Is the time delay faster in
That time delay is again of the order of attoseconds.
Yes, sir. Which is the shorter time delay? The one caused by attosecond
No,
pulses?
they are of the order of attoseconds, and you get pulses. These pulses again, their durations. It is a Fourier synthesis of number of waves. So where do you want to mark the cutoff. So these are not very rigid, very accurate numbers. That is the reason people talk about time pulses of certain durations, which are of the order of attoseconds.
Thank you, sir.
Thank you, sir. Now, I request Professor P.K. Ahluwalia to deliver the concluding remarks.
Thank you very much. Sir, there are two questions. I think, hands have been raised. One is by Gurmeet Singh.
Yes.
And other is by Basav Raja Kagali.
Yes.
Gurmeet, you have to ask the question. Please unmute yourself and ask your question. Gurmeet, are you there?
I don't have any question.
Okay. And what about
Yes, I am there, but I don't have any question.
Okay.
Ahluwalia, we shall have only 2 questions because students here are waiting for the prize distribution. We shall take only 2 questions online. Kagali sir?
Yes, I have a simple
Please.
question.
Welcome.
I have many
welcome
questions,
you.
but the question is there any simple relationship between the frequency of the incident laser light and the attosecond pulses? Is there a simple relationship?
Yes, these are multiples of the original frequency.
No, I mean the laser frequency. How does that influence the attosecond frequency?
Yeah. So the attosecond pulses involve higher harmonics. So they are like overtones. So the original frequency is multiplied by a certain number.
Thank you.
So these are overtones essentially. Any other question?
There is one by Abnish who says, how do we record these observations that we get?
Okay, I will only mention one of the techniques, which is the use of streaking technology. It is used even in cameras. People are familiar with this. But this streaking is carried out by using another, electrical field which is oscillating. And then from the superposition of this phenomenon, you can generate a trace on a detector from which you can estimate the time delay. So it's a very sophisticated technique. It's impossible to give a detailed answer. But essentially, if you look into the literature about streaking methods, you will find the solution there.
Okay, thank you. Thank you, Ahluwalia. Now we are proceeding for the next program. It is now the prize distribution. Now I call upon Sharmishta Sahu ma'am to take over.
So, thank you very, very much for the wonderful lecture, sir. Actually, there is a lot more questions waiting, but I'm really sorry to cut down because girl children have to go back home and it's getting a little late. So I'm really sorry for this. And a very good afternoon after the wonderful lecture on the Nobel. Not able to hear.
Check.
Hello? Hello? Huh? Is it clear now? Yes. Okay, can you hear me? Right, okay. So we really had a wonderful lecture, and soon after that, this is an auspicious day, I would say. We have conducted a number of activities by RC12A, and we have invited the children, the winners, to receive the prize today itself. And luckily, most of them are over here, so we would like to give away the prizes with Professor P.C. Deshmukh, by Professor P.C. Deshmukh to the children. So we'll have that right away. I would like to show the names of the winners on the screen. So please have a look. Win or lose, joy is yours. So anybody who participated in the program should be happy whether he is winning or losing. What does Wilma Rudolph say about it? Winning is great, sure, but if you are really going to do something in life, the secret is learning how to lose. So you must be prepared both ways. RC12A conducted a lot of activities. Some of them were outreach programs. We went out to different schools and conducted activities. Along with that, this year, like last year, we conducted a number of competitions. The competitions were on experimental physics, computational physics, and on essay writing. These were taken care of by enthusiastic assistant professors of different colleges, and they made a set of rules, passed it on in flyers to different colleges, invited all the school children and the teachers to do all these activities based on the rules and regulations, and they were given sufficient time to prepare for them. Mr. Nagendra Prasad BK of KLE College took the responsibility of conducting the regional competition of experimental physics. Mr. Pramod Kumar, assistant professor in BMS College, took the responsibility and conducted the computational physics program very well. And of course, Ms. Kamala Shri, assistant professor in MES College, took up the responsibility of conducting the essay writing for all the school children over here in Bangalore and around. And of course, we conduct NEST year after year. The regional activities are taken care of by the coordinator of the Anveshika of that region. And I took that responsibility and we conducted the NEST exam also. These were taken care of by a number of judges, eminent professors from different universities. I would like to name them who all had done the wonderful job of conducting these competitions. For the computational physics, we had Dr. Jayant Vyasanakare of Azim Premji University and Dr. Durgakala S, Computer Science MES College. Both of them spared their time and gave sufficient time questioning these children, finding out what are the computational techniques that they have used, what are the concepts of physics that they have incorporated in their projects, asked them a variety of questions to understand the problem thoroughly, and then gave their assessment. Then in the afternoon session on 30th of July, we had the finals of the regional competition of experimental physics. Dr. Chetan M of Jain University and Dr. Usharani D, principal of MES College, gave their precious time, came over there and saw all the 5 teams, what they had done. They interrogated them, found out what exactly the innovation was incorporated in their projects, gave them sufficient time to explain their experiments thoroughly, and as a result of that, they spent a lot of time with these 5 teams to find out the exact merit of each of these work. Thank you very much for their presence, and based on their assessment, we have announced the prizes. And of course, the judges for the essay writing were Professor Habibullah of MES College and Professor Krishna Mohan of Maharani's College, Mysore. The essay competitions were conducted. The children were allowed to write the essays. The topic was physics in forensic science. They were supposed to write the essays in their schools or colleges and send it to us. Then the judges made a wonderful rubric to find out so that there is no discrepancy between the assessments. They also check the plagiarism test so that they don't give undue marks to any person, anyone who has copied. And then they made a strategy to evaluate these essays. And fortunately, both their assessments were absolutely similar, showing who all are doing very well. And all based on their judgment, we did the announcement and are now announcing the prizes. The prize winners of the computational physics, there were totally 4 teams. Of them, 4 teams, 2 of them are getting the prize. The first team consisted of 3 students, Panaga N. Pathak, Monica HS, and Yamuna D. All these 3 students belong to 2nd BSc of Maharani Cluster University. The topic was charging and discharging of capacitor, and they stood first. And I request Professor Deshmukh to kindly do the honors of giving away the prizes. These prize winners will be getting a certificate as well as a cash amount. The first prize goes to 3 students, Panaga N. Pathak, Monica HS, and Yamuna D. Yamuna, yes. Thank you. Okay. And the second prize goes to Chaitanya Rani SR of 2nd MSc. She also belongs to Maharani Cluster University. Her topic was auto irrigation. She stands second. Now, looking at the prize winners, and the universities, we realize that there are teachers behind these projects, and they have motivated all the children to take up these projects and do these exercises. So we request Madam Hemalata and Wajiha ma'am, who were their guides, to kindly come up to the stage. Quickly. Okay. Thank you. Okay. Excuse me. The prize winners for the regional competition in experimental physics, again there were totally 5 teams, of which 3 of them are winning. And all the 3 teams belong to different categories. We have 1 winner from the teachers category, 1 team from the school students category, and 1 more from the PG students category. So the teachers who have won are from MES KKPU College and myself, Sumana Rao S. and Sharmistha Sahu. The topic was Beauty of Malice's Law. They get the first. Sir, can I request Shrikanta sir and Somsekar sir to kindly come up to the stage? No? No? Okay. Take it. The second prize goes to the student Sanchita V. Iyer from school. She had done a lovely experiment on transition temperature of ferro to paraelectric material. The third prize goes to Suchika D. Biligere. She is from Mysore University. She did a simple but elegant experiment on self-powered device for glowing LED. The prize winners of the essay writing competitions were many, not just 3, and that is because most of the students, there were totally 19 teams, and most of them were from school. So some teachers in these schools, if you look at the school names, most of them belong to, or in fact all of them belong to MES KKPU College or school, and the college students belong to MES ACS. So all these teachers at the MES institutions took the initiative and motivated their children, as a result of which 19 participants were present, and therefore we decided that we must give many more prizes, not just 3. The first prize goes to Divya Darshan. He is in the first PUC. The second prize goes to a school student of class 8, Sanjana S. Her essay was extremely wonderful, absolutely short and crisp, and beautifully written. Topic is physics in forensic science.
General topic.
General topic, yes. The third prize is shared by 2 students. Sanchita V. Iyer again gets the prize in essay from MES KKPU College. She is in first PUC. And Dhruva KG from second PUC, MES KKPU College. I think Dhruva is not present now. Then there are 2 more prizes for the PG students. Mr. Charan Reddy from second BSc, MES ACS. He is also not here. And the second prize goes to Muskan Pandey from first BSc. She's coming. Just hold on, I will hurry up. But this is not all. All these prize winners plus all the participants were requested to modify their experiments and to participate in the national event. So they went ahead. Most of them had participated in the national event, and they also won prizes in the national event. The national competition in experimental physics, one boy, Rohit Balmukund, he was the winner of NEST in the regional level and had won a prize. He was motivated to participate in the national level, and he went to Jaipur for the convention, 37th convention, and participated in the national level. His experiment was refractive index of water in a plastic box, which he used it as a prism. And he did a wonderful job. I will just show you a picture of it. He got the second prize in the school category. He's received 5,000 rupees, and we are not giving any more prizes over here. But I definitely wanted to announce this. It is a great achievement from a student of class 11 of Bangalore schools, going and participating in the national level and winning a prize. So hearty congratulations to Rohit. And in the teachers level also, But the experiment which had got the prize in the regional level, again got the first prize in the teachers category. Both Sumana and myself got 7,000 rupees from at Jaipur in the 37th annual convention. And there was a creamy layer. We had a national level competition for essay writing. We requested Dr. Usharani D, MES, Principal of MES ACS, to write an essay and submit it. Luckily, she agreed to it, and the last day of submission, she submitted the essay and has bagged the first prize in the teachers category. So hearty congratulations to that. She has really made us proud. This is the picture. If you can see on the right hand side, Rohit is working on this dark room. He has created the dark room with cardboard, and he is doing the experiment in the dark room and showing what is he capable of showing. With white light, he is showing that the red and the blue lights have different refractive indices because they deviate differently, and that separation he is able to show and make a measurement. In addition to that, he also showed that the grazing of the blue light and the red light are different, as a result of which the critical angles are different, and therefore the refractive indices of red and green for water is different. He showed it very beautifully. The coordinator of NCIEP, Dr. Geeta, is watching this experiment, and he got the second prize. The celebrations at the 37th was really great. I don't think I can show it to you. The picture on the left is showing both of us were receiving the prize, and they really did the wonderful celebration by putting a pagadi on top of all the winners and asking them to give a few words about what they have felt about the experiment. So that is what the picture is showing here. And the icing and the cake. This year, there was an award called the RC Exemplar Award given by IAPT Central Office to all the RCs. It was open to all the RCs, people, those who have done good work and were able to showcase their work, got it. And RC 12A was awarded the Uttama Exemplar RC Award this year. We got a citation as well as a cash award of rupees 20,000. Now, of course, this 20,000 is for our RC to extend our outreach programs for the year and reach out to all the unreached students. So that is our responsibility now. So I'm extremely happy that we have got this prize. And this is the left picture is the award, which is showing how much is the cash award. And the right was the citation. The citation shows what are the type of work that we have done, which has been recognized, as a result of which we get the Uttama RC Award. So I'll just read out what is written in the citation. Regional Council RC 12A, Bangalore, of the Indian Association of Physics Teachers wins the Uttama Award for its consistent contribution to popularize physics education. The council organized maximum number of stage shows, Anveshika sessions for experimental physics at various school, college programs, training programs, and enrolling hundreds of students for next examination. The council members also contributed to the IAPT monthly bulletin in the form of articles and reports, signing MOUs with other institutes to promote collaborative efforts and providing resource persons to other RCs, boosting academic efforts and fulfilling the duty of submission of annual financial statement of expenditure on time to the IAPT Central Office are greatly appreciated. This was awarded in the 37th IAPT Convention at Jaipur this year. Thank you very much, and we are really proud that we've got it. So hearty congratulations to all the winners and all the participants of the various competitions. I would request a few of them to share their experience in 1 minute.
Please.
No?
They are waiting.
They're okay? Okay. Acha, okay. I'm sorry for this. I think they are in a big hurry. So, yeah, okay. Thank you.
They are in a big hurry.
I want to congratulate all the participants, those who won the awards and also those who did not win the award. Heartiest congratulations to all the participants, to their mentors, teachers, to the regional council.
Yes.
I think the regional council has done extremely well. I'm very proud to be a part of this.
Thank you so much.
And our deepest gratitude to the parent organization, which is the Indian Association of Physics Teachers, under the leadership of Professor Ahluwalia-ji. I think promotion of physics education by this agency is very inspiring, and I'm sure that it will benefit many students and teachers. Thank you all very much.
Thank you very much. I request the past president, Professor Shrikanta, to kindly give the vote of thanks.
Before that, Professor Shrikanta is our alumni, and he was a professor at National College, Gauribidnur, and we are happy to have him here to give a few introduction of the National College. National Education Society is 100 years plus young, I can say. We started in 1917 with a high school. Later on, for commemoration of Silver Jubilee of the high school, we started National College, which is around 75 years. National College is a well-known organization across the country and across the globe. In America, every 10 kilometers has our alumni. Silicon Valley has large number of alumni of the National College. The alumni of the National College have globally contributed in all sense, for science, for commerce, for arts, and all those things. Leading artists of the state, Vishnuvardhan, and all the majority of the film actors are from here. Cricketers are from here. Scientists are from here. Our Kiran Kumar was our alumni. And we have Bangalore Science Forum. Bangalore Science Forum has conducted more than 3,000 lectures on the same platform. We conducted around 55 summer schools, lecture competitions, and many more. This is a ground. The stage is a very prestigious stage, and you have taken prize on this stage. So let me congratulate you on behalf of the National College. Over to Professor Shrikanta.
Ellargu namaskara. Very good evening to one and all present here. Honorable guest speaker of the day, Professor Deshmukh, and all the friends in the audience. It's a very special day for me. For one reason, the reason is I passed out from this college in 1973, and now it is 2023. So I am celebrating golden jubilee of my graduation. Golden jubilee of my graduation. I passed out from this institution in 1973, 50 years back, and after 50 years, I got an opportunity to stand on the dais and speak to the audience here. I consider it as by luck and this thing, fortune. Second thing is, today, is the birthday of Sir C. Raman. And again, I'm an alumnus of Raman Research Institute, established by Raman. And today we are celebrating the birthday of Sir C. Raman, and I got the opportunity to speak. In fact, there was an invitation for me to attend a program in Raman Institute also. Today they are releasing, the governor, Honorable Governor of Karnataka, is releasing the stamp on this occasion. I had an invitation to attend that program, but I chose this program because I wanted to learn physics and hear from Professor Deshmukh, because I had heard and that Deshmukh is a good speaker. From many of my friends, I had heard that Professor is a good speaker, and that's why I chose to attend this program, sir. And it is really a pleasure to come to the alma mater also. So that's why I chose this to attend your program. So that way I am really lucky on 2 counts, and I'm very happy about that. And we are very happy, and we had a very scholarly talk by Professor Deshmukh. And I don't know, I'm not really capable of commenting on the lecture. It was really scholarly talk. But one thing I want to be honest, Professor Deshmukh has introduced us to the field, the attosecond pulse and dynamics. But to really understand that, I think we need some more information, and we have to spend some more time to understand the intricacies of this autodynamics and all that. But one thing is, we had a very good introduction to the subject. We have been introduced in a very nice manner by Professor Deshmukh. And on behalf of all of us, on behalf of all of you, and also on my own behalf, I extend a grateful thanks to you, sir, for having delivered this talk. And also, you know, Professor Deshmukh has traveled all the way from Tirupati, to deliver this lecture. And we are very grateful to you, sir. It was really enlightening. And we thank you very much on behalf of all of us. Thank you very much. And then we should thank the President of the National Education Society of Karnataka, Dr.HN Subramania, and also Sri Venkat Shiva Reddy, Honorary Secretary of NES Karnataka, Sri B.S. Arun Kumar, Honorary Secretary of NES of Karnataka, and Sri Sudhakar Isturi, Chairman of National College Basavanagudi, for having given this place to conduct this program by the Indian Association of Physics Teachers. And also, we are very grateful to the principal, very dynamic principal. Of course, we have been, Dr. Y.C. Kamala, we have been friends for the last almost 30 years or more than that, 30 decades. And I'm very happy that, you know, and not just, she is also a physics teacher. See, that's very important. She is also a physics teacher. And once upon a time, when I was the principal of college, there were about 10 principals from the physics department in the Bangalore University. So now that number has come down. Now it's, So we are very grateful to Madam Dr. Y.C. Kamala for having taken the initiative, and also for arranging this program, taken initiative. In fact, when I came at 4:30, she was eagerly waiting for the guest speaker and all that. And then immediately she asked me to go to the chambers and all that, and occasion to meet the president and secretary of the association also. So we are grateful to Dr. Kamala for having taken the initiative to conduct this program. And then I don't have to tell the audience about the dynamism of Sharmishta Shahu. You know, Sharmishta Shahu is the present secretary of RC12A. Some people must be wondering, what is this RC12A? RC12A. So I tell you, this Indian Association of Physics Teachers is an all-India body. And then state-wise, there are regional councils. Regional councils are there. And in Karnataka, this Karnataka is RC12A. RC12 means it's Karnataka, region council Karnataka. But this 12A, actually there is one RC12A. They have got, madam, it is 12 is in somewhere in Gulbarga. RC12? No, 12 is. RC12 is headquartered in Gulbarga. It's very far from Bangalore, very far. It's very difficult for us to coordinate the activities and all that. And therefore, we wanted to start a subgroup of that RC12, which is in the southern part of Karnataka. And therefore, we opened one more unit here, and that's called RC12A. And of course, under the leadership of Sharmishta Shahu and also Dr. Anand Kumari, president of the IC12A, they are doing an excellent job. And we thank 12A and also President Dr. Anand Kumari and also Sharmishta Shahu for having taken the initiative. They are conducting so many programs which you have already seen it. And we thank both of them for the good work that they are doing and also for conducting this program. And then We thank the compeers of the program. I don't know their names, but anyway, I thank the students of this comparing the program for having compared the program. And of course, I will be failing in my duty if I don't thank all of you. Now we see many professors, very senior professors are here, and many teachers are there. Many my teacher colleagues are here, and students are here. And in fact, this entire program is meant for teachers and students only. And it's a good thing that I was really apprehensive. In fact, I spoke to Dr. Kamala also. ಏನು ಮಳೆ ಬರ್ತಾ ಇದೆ, ಏನು ಎಷ್ಟು ಜನ ಬರ್ತಾ ಇರೋನೋ ಗೊತ್ತಿಲ್ಲ ಅಂತ ನಾನು ಸ್ವಲ್ಪ ಆ್ಯಡ್ ಮೈ ಓನ್ ಅಪ್ರಹೆನ್ಷನ್. ಬಟ್ ದಿ ಹಾಲ್ ಈಸ್ ಫುಲ್ ಆ್ಯಕ್ಚುಲಿ, ದಿ ಹಾಲ್ ಈಸ್ ಫುಲ್. ಸೊ ಇಟ್ ರಿಯಲಿ that shows the popularity of our speaker. There is a popularity of the speaker, and also the interest that this particular subject has created in the minds of the students and teachers. In fact, when the Nobel Prize was announced, I was also for a second, I knew what is an attosecond, but what is this attosecond dynamics? I had to really do some homework. And so that way this created a lot of interest among the students and also teachers of physics. And that's why you find, when large number of teachers and students have come in large numbers, and therefore we thank all of you for having attended this program and made this program successful. And I once again thank the management of NES of Karnataka and the principal and the staff of Vice Principal Ramesh is here. He was here actually. Okay, we thank all the management of NES of Karnataka and also the principal, vice principal and other faculty members of National College for having taken the initiative to organize this program. And once again thank all of you, and we hope that the next program will be held here also in the same program at the same hall, because it's very convenient. It is very convenient in the heart of the city, and we expect the similar support and cooperation from our physics principal, Dr. Kamala. Thank you very much. Thank you.